All right, let's look at phase diagrams and factors affecting solubility, how to understand them and to use them. So you've been doing things with states of matter since the second grade and maybe even earlier. So what we're looking at is how do we represent what's going on here when things are a little bit more complicated. And for that we use phase diagrams. So with phase diagrams, I want you to be able to look at some similarities and differences. There's always a solid, liquid, gas portion. However, that may vary quite a bit depending upon the substance. Each line represented is where both states of matter that border exist. So in between solids and liquids, you have both solid and liquid gas, or solid and liquid, at that pressure and that temperature. There's always a pressure and temperature component involving these. The triple point is where all of those exist at that particular pressure and temperature. Also where called a supercritical fluid exists. I was just listening to one of my podcasts involving chemistry, and they think that at room temperature water, there are two states of matter of liquid, a high dense and a low dense, which makes it a supercritical fluid at room temperature. There's been some recent developments in that. You want to make sure you get some practice on Pearson if you're comfortable navigating them, such as if things changed with pressure or temperature, what would that do to the state of matter and how would that change? So get used to seeing them and doing them. Otherwise, it's pretty straightforward about what you're kind of asked to do. Most interesting property of water is that it can dissolve solids and gases into itself, making aqueous solutions. That's what we're going to be focusing on. And we've already seen a little bit of this before, but we're kind of adding to it. So ask yourself, why is the case for being different for a solid and for a gas? Why would they dissolve differently? And that has to do with intermolecular forces and attractions. In a solid, when you warm it up, a solid, more of it generally dissolves, with a few exceptions, like something super large, like cerium? I think Ce is cerium. It's been a long time for that one. But most of it goes up. And that's because you need more energy to break the attractions between ions. So the more energy you have, the higher temperature, the more that you can dissolve. In a gas, though, we have things that are different. If you look at all of these gases are going to be covalent compounds. They're never really going to be any kind of ionic compounds because they have their melting points way too high. So as temperature increases, you see the solubility goes down. It's actually the opposite of solids. And that's because gases are covalent compounds, so intermolecular forces are super necessary in order to dissolve that. And the idea is that at higher temperatures, the solvent, let's say water, is going to be moving around much, much more, and that enables the idea of getting out of the way so these more buoyant gases, because gases and liquids, all gases are going to be buoyant and float, are going to come out of solution and not likely to stay in the solution and dissolve. You can look also at the comparisons. You have, for solids, you're talking about grams per 100 grams of water, and significant amounts. Over here, you're talking about milligrams, and those are small amounts of milligrams per 100 grams of water. So keep that in mind. Pretty big difference. At the higher the temperature, the less dissolves. There's one other aspect too that plays a role, and that's polarity. So when it comes to polarity, we're going to focus just on like the gases, because the ionic compounds, of course, those are full-blown charges in a polar water, so there's high attractive forces there. But let's take a look at these. Now, these are gas constants. You're not calculating these, but I want you to kind of use these as an idea to compare. So this is the amount of moles at 1 atm per liter. So this is kind of like the molarity per the atmosphere, per the same amount of pressure. So things that are nonpolar, your hydrogen, nitrogen, and oxygen, are very small. Very small. Okay? It doesn't go with the idea of molar masses. There's always more complexities going on, but we can see very small because they're nonpolar. So there's less attracting them to stay into that solution. Something like CO2 has polar bonds, even though it is nonpolar, so we can see that go up. Something like CH4, again, nonpolar, and these difference in polarity of bonds is also going to be quite low, hence why it's still pretty small compared to CO2. Something like hydrogen sulfide, very similar in the idea that this is polar, but those electronegativity differences are so small, it doesn't really create that difference. Then we get to something like ammonia, NH3, hydrogen bonded. Huge difference of solubility, right? This would take about 59 moles in one liter at the atmospheres there. So a huge amount due to the attractive forces. So keeping these things in mind, when we look over here at the chart, something like nitrogen and oxygen, a bigger electronegativity difference than something like carbon monoxide. Actually, it's a little less. But there's something about it that plays to where it's going to have more attractive forces, probably because these are more electronegative, and so they kind of have more attractive forces to the water particles. And we have our nonpolar things, nonpolar, but it's also a little bit more. So I just want you to grasp the idea that polarity plays a role. So if we had to choose between things, as this was a list, which one would more dissolve in water, again, you're looking for those attractive intermolecular forces being expanded to the idea of gas dissolving in liquid. Get some practice about these just so you have these down, so when you come across a question, you can attack it very simply and easily. Let me know what questions you have. Talk to you soon.